they do so differ. The corresponding assembly languages reflect these differences. Multiple sets of mnemonics or assembly language syntax may exist for a single instruction set, typically instantiated in different assembler programs. In these cases, the most popular one is usually that supplied by the CPU manufacturer and used in its documentation. Two examples of CPUs that have two different sets of mnemonics are the Intel 8080 family and the Intel 8086/8088. Because Intel claimed copyright on its assembly language mnemonics, on each page of the documentation published in the 1970s and early 1980s, at least, some companies that independently produced CPUs compatible with Intel instruction sets invented their own mnemonics. The Zilog Z80 CPU, an enhancement of the Intel 8080, supports all the 8080 instructions plus many more. Zilog invented an entirely new assembly language, not only for the new instructions but also for all of the 8080 instructions. For example, where Intel uses the mnemonics MOV, MVI, LDA, STA, LXI, LDX, STARKS, LHLD, and SHLD for various data transfer instructions, the Z80 assembly language uses the mnemonic LD for all oft-hem. A similar case is the NEC V20 and V30 CPUs, enhanced copies of the Intel 8086 and 8088 respectively. Like Zilog with the Z80, NEC invented new mnemonics for all of the 8086 and 8088. Instructions. To avoid accusations of infringement of Intel's copyright. It is questionable whether such copyrights can be valid, and later CPU companies such as AMD, NB5, and Cyrix republished Intel SX86/IA32 instruction mnemonics exactly with neither permission nor legal penalty. It is doubtful whether in practice many people who programmed the V20 and V30 actually wrote in NEC's assembly language other than Intel's, since any two assembly languages for the same instruction set architecture are asymorphic, somewhat like English and Pig Latin. There is no requirement to use a manufacturer's own published assembly language with that manufacturer's products. Language design. Basic elements. There is a large degree of diversity in the way the authors of assemblers categorize statements and in the nomenclature that they use. In particular, some describe anything other than a machine mnemonic or extended mnemonic as a pseudo-operation, pseudo-op. A typical assembly language consists of three types of instruction statements that are used to define program operations of code mnemonics. Data definitions. Assembly directives. Opcode mnemonics and extended mnemonics. Instructions, statements, in assembly language are generally very simple, unlike those in high-level languages. Generally, a mnemonic is a symbolic name for a single executable machine language instruction, an opcode, and there is at least one opcode mnemonic defined for each machine language instruction. Each instruction typically consists of an operation or opcode plus 0 or more operands. Most instructions refer to a single value or a pair of values. Operands can be immediate, value coded in the instruction itself, registers specified in the instruction or implied, or the addresses of data located elsewhere in storage. This is determined by the underlying processor architecture. The assembler merely reflects how this architecture works. Extended mnemonics are often used to specify a combination of an opcode with a specific operand E.G. The system /360 assemblers use B as an extended mnemonic for BC with a mask of 15 and NOP. NO operation do nothing for one step, for BC with a mask of 0. Extended mnemonics are often used to support specialized uses of instructions, often for purposes not obvious from the instruction name. For example, Many CPUs do not have an explicit NOP instruction, but do have instructions that can be used for the purpose. In 8086 CPUs the instruction XCHG-AXAX is used for NOP, with NOP being a pseudo-opcode to encode the instruction XCHG-AXAX. Some disassemblers recognize this and will decode the XCHG-AXAX instruction as NOP. Similarly, IBM assemblers for System/360 and System/370 use the extended Mnemonics NOP and NOPA for BC and BCR with zero masks. For the SPARC architecture, these are known as synthetic instructions. 22. Some assemblers also support simple built-in macro instructions that generate two or more machine instructions. For instance, with some Z80 assemblers the instruction LDHLBC is recognized to generate LDLC followed by LDHB. 23. These are sometimes known as pseudo-opcodes. Mnemonics are arbitrary symbols. In 1985 the IEEE published Standard 694 for a uniform set of mnemonics to be used by all assemblers. The standard has since been withdrawn. Data directives. There are instructions used to define data elements to hold data and variables. They define the type of data, the length and the alignment of data. These instructions can also define whether the data is available to outside programs assembled separately, or only to the program in which the data section is defined. Some assemblers classify these as pseudo-ops. Assembly directives. Assembly directives, also called pseudo-opcodes, pseudo-operations or pseudo-ops, are commands given to an assembler directing it to perform operations other than assembling instructions. 16. Directives affects how the assembler operates and may affect the object code, the symbol table, the listing file, and their values of internal assembler parameters. Sometimes the term pseudo-opcode is reserved for directives that generate object code, such as those that generate data. 24. The names of pseudo-ops often start with a dot to distinguish them from machine instructions. Pseudo-ops can make the assembly of the program dependent on parameters input by a programmer, so that one program can be assembled in different ways, perhaps for different applications. Or, a pseudo-op can burst to manipulate presentation of a program to make it easier to read and maintain. Another common use of pseudo-ops is to reserve storage areas for runtime data and optionally initialize their contents to known values. Symbolic assemblers let programmers associate arbitrary names, labels or symbols, with memory locations and various constants. Usually, every constant and variable is given a name so instructions can reference those locations by name, thus promoting self-documenting code. In executable code, the name of each subroutine is associated with its entry point, so any calls to a subroutine can use its name. Inside subroutines, go-to destinations are given labels. Some assemblers support local symbols which are often lexically distinct from normal symbols, for example, the use of $10 as a go-to destination. Some assemblers, such as NASM, provide flexible symbol management, letting programmers manage different namespaces, automatically calculate offsets within data structures, and assign labels that refer to literal values or the result of simple computations performed by the assembler. Labels can also be used to initialize constants and variables with relocatable addresses. Assembly languages, like most other computer languages, allow comments to be added to program source code that will be ignored during assembly. Judicious commenting is essential in assembly language programs, as the meaning and purpose of a sequence of binary machine instructions can be difficult to determine. The raw, uncommented, assembly language generated by compilers or disassemblers is quite difficult to read when changes must be made. Macros. Many assemblers support predefined macros, and others support programmer-defined, and repeatedly redefinable, macros involving sequences of text lines in which variables and constants are embedded. The macro definition is most commonly, NB6, a mixture of assembler statements, for example, directives, symbolic machine instructions, and templates for assembler statements. This sequence of text lines may include opcodes or directives. Once a macro has been defined, its name may be used in place of a mnemonic. When the assembler processes such a statement, it replaces the statement with the text lines associated with that macro, then processes them as if they existed in the source code file, including, in some assemblers, expansion of any macros existing in the replacement text. Macros in this sense date to IBM autocoders of 1950s.25, NB7. Macro assemblers typically have directives to, for example, define macros, define variables, set variables to their result of an arithmetic, logical or string expression, iterate, conditionally generate code. Some of those directives may be restricted to use within a macro definition, for example, mexit in LASM, while others may be permitted within open code, outside macro definitions, for example, AIF and copy in LASM. In assembly language, the term macro represents a more comprehensive concept than it does in some other contexts, such as the preprocessor in the C programming language, where its hash-defined directive typically is used to create short single-line macros. Assembler macro instructions, like macros in PL/I and some other languages, can be lengthy programs by themselves, executed by interpretation by the assembler during assembly. Since macros can have short names but expand to several or indeed many lines of code, they can be used to make assembly language programs appear to be far shorter, requiring fewer lines of source code, as with higher-level languages. They can also be used to add higher levels of structure to assembly programs, optionally introduce embedded debugging code via parameters and other similar features. Macro assemblers often allow macros to take parameters. Some assemblers include quite sophisticated macro languages, incorporating such high-level language elements as optional parameters, symbolic variables, conditionals, string manipulation, and arithmetic operations, all usable during the execution of a given macro, and allowing macros to save context or exchange information. Thus a macro might generate numerous assembly language instructions or data definitions, based on the macro arguments. This could burst to generate record-style data structures or unrolled loops, for example, or could generate entire algorithms based on complex parameters. For instance, a sort macro could accept the specification of a complex sort key and generate code crafted for that specific key, not needing the runtime tests that would be required for a general procedure interpreting the specification. An organization using assembly language that has been heavily extended using such a macro suite can be considered to be working in a high-level language, since such programmers are not working with a computer's lowest-level conceptual elements. Underlining this point, macros were used to implement an early virtual machine in Snobble for 1967, which was written in the Snobble implementation language, SIL, an assembly language for a virtual machine. The target machine would translate this to its native code using a macro assembler. 26. These allowed a high degree of portability for the time. Macros were used to customize large-scale software systems for specific customers in the mainframe era and were also used by customer personnel to satisfy their employers' needs by making specific versions of manufacturer operating systems. This was done, for example, by systems programmers working with IBM's Conversational Monitor System /virtual machine, VM/CMS, and with IBM's real-time transaction processing add-ons. Customer Information Control System CICS, and ACP/TPF, the airline/financial system that began in the 1970s and still runs many large computer reservation systems, CRS, and credit card systems today. It is also possible to use solely the macro processing abilities of an assembler to generate code written incompletely. Different languages, for example, to generate a version of a program in COBOL using a pure macro assembler program containing lines of COBOL code inside assembly time operators instructing the assembler to generate arbitrary code. IBM OS/360 uses macros to perform system generation. The user specifies options by coding a series of assembler macros. Assembling these macros generates a job stream to build the system, including job control language and utility control statements. This is because, as was realized in the 1960s, the concept of macro processing is independent of the concept of assembly, the former being in modern terms more word processing, text processing, than generating object code. The concept of macro processing appeared, and appears, in the C programming language, which supports preprocessor instructions to set variables, and make conditional tests on the values. Unlike certain previous macro processors inside assemblers, the C preprocessor is not Turing complete because it lacks the ability to either loop or go to, the latter allowing programs to loop. Despite the power of macro processing, it fell into disuse in many high-level languages, major exceptions being C, C++, and PL/I, while remaining a perennial for assemblers. Macro parameter substitution is strictly by name. At macro processing time, the value of a parameter is textually substituted for its name. The most famous class of bugs resulting was the use of a parameter that itself was an expression and not a simple name when the macro writer expected a name. In the macro foo, macro loader *b, the intention was that the caller would provide the name of a variable, and the global variable or constant would be used to multiply a. If foo is called with the parameter AC, the macro expansion of loader *b occurs. To avoid any possible ambiguity, users of macro processors can parenthesize formal parameters inside macro definitions, or callers can parenthesize the input parameters. 27. Support for structured programming. Packages of macros have been written providing structured programming elements to encode execution flow. The earliest example of this approach was in the Concept 14 macro set, 28, originally proposed by Harlan Mills, March 1970, and implemented by Marvin Kessler at IBM's Federal Systems Division, which provided if/else/end if and similar control flow blocks for S/360 assembler programs. This was a way to reduce or eliminate the use of goto operations in assembly code, one of the main factors causing spaghetti code in assembly language. This approach was widely accepted in the early 1980s, the latter days of large-scale assembly language use. IBM's High-Level Assembler Toolkit, 29, includes such a macro package. A curious design was A-Natural, a stream-oriented assembler for 8080/Z80 processors from White Smiths Limited. Developers of the Unix-like Idris operating system, and what was reported to be the first commercial C compiler. The language was classified as an assembler because it worked with raw machine elements such as opcodes, registers, and memory references, but it incorporated an expression syntax to indicate execution order. Parentheses and other special symbols, along with block-oriented structured programming constructs, controlled the sequence of the generated instructions. A-Natural was built as the object language of a C compiler, rather than for hand coding. but its logical syntax won some fans. There has been little apparent demand for more sophisticated assemblers since the decline of large-scale assembly language development. 30. In spite of that, they are still being developed and applied in cases where resource constraints or peculiarities in the target system's architecture prevent the effective use of